Hello and welcome to this new series of tutorials on discrete time signal processing in Matlab. So in this particular tutorial, we'll be learning to define some basic signals, and then in the upcoming tutorials, we'll be learning to perform basic signal processing operations on them. So let's first define a signal. So discrete time signal has a time index and an amplitude index, an amplitude variable, right? So a time variable is generally defined using n. Suppose our signal that a discrete signal has values between time index 2 to 5, right? So it's 0 otherwise, but it has only values between time index 2 to 5, right? And so this is how you specify the time index. A time index is generally a range that has integer values, all the integer values between the range, between the starting point and the ending point. So here the starting point is 2, the ending point is 5, and it time index n. Now because of this use of colon, it gives you all the values, all the integer values between 2 and 5, right? So once you have the time index, then you need to specify the amplitude index. So suppose you have this signal. Um, Suppose your signal is something like that. So you have only 4 time indexes. So you need to specify 4 values here. So your values in x and values in n should be equal, right? So, uh, so and now you can use this stem plot option to plot this discrete signal n comma x. So before you, it is always good before we plot, it's always good to close previous figures. Generally you have you have some figures open already, and so now you press enter and you will get this plot. So as you can see, here at time index 2 you have value -1, and as you can see the time at time index 2 you get this stem of amplitude -1, and similarly at time index 3 you have this stem of amplitude -2, and similarly at time index 4 you get this stem of amplitude 0.5 -0.5, and here you get this stem of amplitude 1, right? So as you can see here, right? And so this is how you define a discrete signals. You could also define discrete signals using built-in MATLAB functions. Suppose your signal is your signal that you want to define is based on a cos function or a sine function. So then you can use those functions in MATLAB to basically construct your signal here. Suppose let's keep the time index same for this new signal that we want to define x1, and let's say it is a sine function, sine of n, right? So once you press enter, you'll get this new signal at so this is a workspace, and here you see all the variables, all the new variables, or all the variables that you have defined, and the corresponding values, right? So as you can see the values for all these time indexes. So since the time index has 4 values, the x1 will also have 4 values, right? So sine will be evaluated on all of these values. So sine 2 is 0.9093, sine 3 is 0.141, and this is similarly sine 4 is this, and sine 5 you have this final value that is 0.95, and it goes. So so let's stem it. So this time when you, so since this new signal is x1, so but if you, so now if you press enter, we'll lose the previous plot. So in order to preserve the previous plot, and you need to specify this figure command that basically reserves a new space for this plot. So as you can see, for this time, once you use this figure command, uh, a new figure 2 is opened, and here you have been able to, you have plot this new signal. as you can see, this is sinusoid, but here you don't see that trend. And we know that sinusoids are basically defined on all time indexes. These are basically signals which have values on all time indexes. So you could see this signal on a larger time range, right? So let's change the time index. Let's make it -10 to 10, right? So, and now evaluate this sine function again, and you will see and then now you plot this x1 again, and here same signal with increased time indexes is um you can see this trend of sinusoidal trend in a much better visualization, I should say, of the sinusoid signal. Now if you add this frequency into it, suppose it has this omega naught frequency. So now let's first define omega naught. Say omega naught is 0.1 steric pi, right? And now let's define x1 again, right? So and now let's stem it, let's plot it, and here you see this sinusoid. So with this new frequency, you get this signal. So by changing the frequency, you will see the signal will change. So if you change omega naught to 0.25 pi, now you're increasing the frequency, which means the oscillations will be faster now. So you could just maybe evaluate the x1 again with new omega naught and now stem it. And here you go. You see that the oscillations are much faster now. The previous case, as you can see, oscillations here you see only two oscillations, rather one oscillation, and here you see multiple oscillations, maybe two or more than two. So you could also use cost function. You could also use maybe exponential function. Let's use exponential function to define x2. Exp n, right? And so exponential function is right, an increasing function. You will, so x2 would be an increasing function now. So if you stem x2, you will get an increasing function. So in case of negative values, the function will have very small values which will be close to 0, and in case of positive values, the function will have higher values. The values will increase exponentially, right? So at 0 the value is close to 0, but as you go till 10, the value increases sharply, 2 raised to power 2.5 raised into 2 raised to power, sorry, 10 raised to power 4. So very high values is, right? And similarly, you could also define you can also define an impulse, a delta, right? So delta, suppose, is a function that has one on 0, time index 0. So you can define this by just saying that n delta should be 1 at time index n is equal to 0. So when time index n is 0, delta should be 1. So as you can see, this equal to twice is a logical operator, and this particular operation is an if command. And once you press this, you get this new delta that when you plot it, when you stem it, you will see so you will see 1 on 0 only. So this particular, to understand this particular command, you need to understand that this part is a logical operation that is basically an if statement, which means this if statement is true when this n, the value of n is equal to 0, and we know there is only one index where a value of n is 0, that is the index 11, I guess. So let's just click on this n. So here at the 11th index of this vector is 0, right? So you will get, so at this index you will get true, right? And at all these other indexes you will get false, right? So false is 0, true is 1, right? And so now if you double click on delta, you will get 1 only on the 11th index. So what you are doing here is that you are applying this n if statement on this vector n, and the result of this if statement is stored in delta, this new variable delta. So so this if statement is only true at 11th index, that is, that contains 0, because it says the if statement is only true if n is equal to 0, and the result, that is the false or the true value, is stored in delta. So as a result you get this impulse function, right? So once you plot it, you get see that this is an impulse which has a 1 at index 0. You can also define this using this zeros function. So suppose you want to define this delta, and you want, so first you define this number of zeros, and so you say that's length of n, to define as many zeros as there are indexes in n, right? So if you want, you say define zeros as many as the length of n, or rather the size of n. So it's a vector, you will, so size of n is the, like, it will give you the number of rows and number of columns in n. So it, as you know, in n we have 1 row and 21 columns, so you'll get 21 zeros, right? And now you need to put 1 at the value where n is equal to 0, and so here you specify delta of n equal to 0, right? So you, so the now you are specifying this if statement within the parentheses of the index parentheses of delta, right? And you say this is equal to 1, right? What will happen here? So when this index n is equal to 0, you'll get 1. So again, so now if you see this delta, you'll get this 1 at this index where n is 0, right? Again, when you plot it, you will see this 1 at index 0, right? There are multiple ways to define it. These are the two which I have just specified to you. Okay, so you can also define a step function using similar methodology. So you define a step function u by applying an if statement on n again, right? So you say you specify a condition that is true for indexes 0 and onwards, like, so index is 0 and greater. So you say n is greater than equal to 0. So if you specify this particular if statement on n, so this statement will be true for indexes 0 and the indexes which are greater than 0, right? So that, and you know true means 1. So the result of this logical operation will be stored in u, right? So this logical operation will be performed on each and every index of n. So index has, so n has 21 values. So for every value of n, this if statement will be evaluated by this Matlab, and the result will be stored in u, right? So for every value, for every index. So you get this resulting signal that has zeros on initial 10 indexes, because the initial 10 indexes are -10 to -1, so which do not satisfy this condition, right? This condition is basically n is greater than or equal to 0, right? So uh, so this time we have just performed it, but we have not stored it in U. So now let's press enter and this will be stored in U, right? Now let's stem it. Figure stem n comma x and this n comma u, right? And here you are. So you get this step function, right? And if suppose the n is changed, suppose n is -100 to 300, right? Suppose this is the new n. You can create both of these signals the same way. The first, we just run this command, this or this requires running of this delta zeros, delta equal to zeros command, and then this command, but this one is much easier. So once you evaluate it, you will get this delta that will have 401 indexes, and there will be and when you stem it, you will see it will have it will be an impulse. So let's stem it. As you can see, there are zeros on all the locations, but there is this one only on index 0, right? Similarly, if you evaluate this particular command, you'll get a step function. Again, I did not use the suppressor, output suppressor, that is semicolon, so you can see all the output here, but let's just do this. And now you just use the stem operation to see the output, and as you can see, the output is 1 after 0. So this is very easy. These two signals are very easy to generate using this format, right? Okay, thank you very much.